All right, our first two problems, number 9 and 10, say to identify the domain and range from the graph that's given, and then also find these function values. So let's start with domain and range. First of all, it's understood that there are arrows on the ends of these lines here because they don't have points plotted like they do at the beginning of each ray. So the domain, you always start left to right. The domain of this left piece would be from negative infinity up to and including the x value 1. And then if you look at this second piece, the second piece picks up at 1, not including 1, carries out to infinity. But you have to simplify this. You can't just leave this here. Because if I tell you to shade this domain on a number line, you'd be shading the entire number line, right? Negative infinity to 1, and then even though 1's not shaded here, it's shaded here. So really, the domain is all real numbers. And then as far as the range, the lowest point is -2, not including, -2. And now this branch goes all the way up to infinity. The other one starts from 1 to infinity, but if we just say everything from -2 to infinity without including -2, that encompasses the second piece of that function too. So there's our range. And then function values for this one. Remember, if you have an equation, f of 2 means plug in 2 for the x and get a value. On a graph, it means when x is 2, what is y? So when x is 2, y is 0, function value is 0. To the right, f of 1, when x is 1, the function value is 1. When x is 3, now for this one, we're going to have to do a little bit of work. When x is 3, does it look like 1? Does it look like something else? Luckily, this is a line, and we started off the year being able to figure out equations of lines, right? I know the points, scroll this down a little bit. I know the points 1, -2 is quote unquote on the line, meaning it's plotted. Even though it's not on the line, I can use it to figure out slope. And I know 2, 0 is on there. So what's the slope for when we're at x equals 3? So the slope here is -2 minus 0 over 1 minus 2. -2 over -1 is a slope of 2. And then you can either use an equation here, or you can say, well, let's just use the equation. So we could just say like y minus 0 equals 2, x minus 2. So I want to know what's the value when I put in 3. 2 times 3 minus 2 is 2. So yeah, see, like where I plotted my point was off a bit. I guess if I look at it more closely now, I should have plotted it there. So maybe you did a good job of kind of estimating that that was 2, but we can prove it mathematically because these are just linear segments. And I'll do something similar with f of -1. So f of -1, let's see if I can place this better. It looks to be 3. But we can check that kind of quickly. This slope is negative, remember, and I can see a point at 0, 2, and there's this point at 1, 1. So I can see that that slope is down 1, right 1, so that's a slope of -1. And so if I just continue with that from the point 0, 2, I can go up 1, left 1. I will be, when x is -1, I will be at 3. Or I could come up with an equation like I did for the previous problem. The reason I did that was because I was thinking I could have also just counted slope, but the way I drew my point threw me off. Okay, for number 10, we've got this graph that has no arrows on it. It has finite endpoints, and it has like a ceiling right here. So the domain, each of these marks are 1s. The domain goes from -4 to 4, and we include the endpoints. The lowest y value on this graph is 0. And the highest is right here, which is at 4. So it looks to me like this is the square root of 16 minus x squared. I don't know that for sure. We're not told this is a perfect semicircle, but I'm just going to keep that in mind when I go to evaluate. function values. I don't need an equation for f of -4. That's 0. F of 0 is 4. But for f of 2, I might be wondering, like, yeah, what is that? It doesn't look like it's 3. It looks like it's a little bit higher than 3 and not quite 4. So that's where I would say, well, I'm going to use this educated guess to say y is probably about the square root of 16 minus 2 squared. So square root of 12. Again, I don't know for sure this is the equation, but a half circle with a radius of 4 would be this equation here. And if you're not sure where I got that, we will see this a lot popping up. I can't remember if I've done it in previous notes or not at this point, but remember equations of circles, just basic equations of circles. X squared plus y squared equals r squared. In this case, r is 16. Solve that thing for y. And the reason I just have positive is because all of these y values are positive. So this is something, this equation, knowing this graph, really useful for calculus. If we have to find the area underneath that, we're just finding the area of a half circle. Oh, and I almost forgot about f of 4. That is also 0. Okay, looks like we're finding domain and range. We're not given graphs for these. You're welcome to sketch graphs for these. Our next section in chapter 1 is all about kind of parent functions and graphs, but you should be familiar with a lot of these, especially quadratics and parent functions from Algebra 2. And if you're not, like I said, we're going to be practicing soon. This is quadratic. Quadratic, I need to pay attention to which way the parabola is opening. It's opening down because it's negative 2x squared. So quadratic domains are all real numbers. A quadratic range is not all real numbers, depending on which way it opens. You've got like a ceiling in this case. I've got a high point at the vertex, and then it goes to negative infinity. So negative infinity up to, what is that high point? This graph opens down. It's been shifted down 3 units, so that's a better sketch of what the graph would look like. So the highest point on there is negative 3. And then the x squared minus 1 graph, maybe I'll draw this a bit more accurately to begin with. It opens up, shifted down 1, something like that. Domain is all real numbers. The sketch is helpful for the range only. So in this case, the low point is the negative 1, and then it opens up to infinity. And then 14, and this is what I was saying, it's useful to get in the habit of, if you see the square root of a perfect square minus x squared or t squared or whatever, that is a half circle. And the radius is the square root of this number. So this is the graph that we had before, where it goes to negative 4 on the left, 4 on the right. It hits 4 on the y-axis. And so the domain is negative 4 to 4. And the range is 0 to 4. Now we will be doing quadratic inequalities and things like that, but this one is kind of nice to just have that in your mind, that that is the equation of a half circle, where the half circle is sitting above the x-axis. Absolute value graphs. This one has been shifted to the right 5 units. And then remember this number out here, we'll talk about this in a couple of days, but that's really just the slope. Like think plus or minus slope for each side of the absolute value. So if it's negative, the absolute value graph is opening down, and it's got the slope of like plus or minus 1/4. The domain for an absolute value is all reals. The range in this one is negative infinity up to 0, including 0. All right, for 20, we've got all these parts on 20. I tried to write out what they were so I don't have to flip back and forth. So we're given this piecewise graph. It's linear on the left of 0, and it's a quadratic that opens down on the right. So what's the domain? Again, this graph is understood to have arrows. So this graph goes from negative infinity to infinity. There are no gaps or jumps or holes here. So all real numbers. Excuse me. The range, you always go bottom to top. So this graph goes down to negative infinity, and then its highest point is 4. Part C says values of x for which f of x equals 0. Another way to think about this is what are the x-intercepts, or what are the zeros of the function. So take a look at the graph. Where does this hit the x-axis? We can confirm this with our equations too if we're not quite sure. Each tick mark is not 1 unit, each tick mark is 2. Take note of that. So x equals negative 4, and that works with the line. And then x equals 2. So make sure you don't call that 1, that's 2. 4 minus 2 squared is going to be 0. And then part D says f of 0. So remember, this is basically saying what's the y-intercept. When x is 0, what is y? So that's 4. What is the value of f at x equals 1? Give us coordinates. So this is saying what's f of 1? So f of 1, we don't have that on here, right? That's not an easy point on our graph. But remember, we have an equation that says when you're plugging in an x value greater than 0, you're on the 4 minus x squared piece of the function, which we can see from the graph. 4 minus 1 squared is 3. And then give that as a coordinate or an ordered pair. So x is 1, y was 3. All right, and then this says f is negative 3, f of negative 3. So I'm just checking I want to confirm the coordinates of the point on the graph f at which x is negative 3. Oh, okay. So this is just another way to ask us find f of negative 3, basically. So remember, f of negative 3 is like over here. You're on the linear section. So you're plugging into the f of negative 3. You're plugging into the x plus 4. So you should get 1 for that. So the ordered pair is negative 3, positive 1. Okay, 21's question. In 17 through 20, so for 20, what are the values you found in part C referred to graphically? So I think I actually wrote this down. Yeah, what are they referred to graphically? So on the graph, we call them x-intercepts. I think I wrote this out more in the key that I post, but x-intercepts when f of x equals 0. And then 22 says, what are the values you found in part D referred to graphically? Again, I kind of got ahead of myself. So part D, find f of 0, that was the y-intercept. It's possible for a function to have more than one x-intercept, but it's not possible to have more than one y-intercept. So I shouldn't put an S on that. If it's a function, because remember, if you had more than one y-intercept, you'd be failing the vertical line test. So just one of those. Speaking of vertical line test, that's the next section. Now I didn't erase all of my work for these because these are pretty quick problems. Use the vertical line test to determine whether y is a function of x. Describe how you can use a graphing utility to produce the graph shown. So I don't need a paragraph for this. I just want you to be able to type this stuff in. So this is really just saying to graph this, figure out how you're going to isolate and get it to be y equals. So I would add y squared over to the right side, and I would subtract 1 over to the left side. I would square root both sides. And remember that generates a plus or minus. So to get this in my graphing calculator, let's just say in y1, I'm going to put the positive square root of x minus 1. And in y2, I'm going to graph the negative square root of x minus 1. And you can test that out if you want to see if you get the graph that they show here. Y is not a function of x. So this is not a function because it's failing the vertical line test. Every x gives us a plus or minus version of the y. All right, and then the next one, we're looking at 26. So vertical line test to begin with. This passes the vertical line test. X equals 0 is not in the domain. You can kind of tell here, there's this graph, there's a vertical asymptote there. Also, if you just plug 0 in for X, 0 equals 0 minus 1, that's not a true statement. So that's another reason why 0 can't be in the domain. Okay, to graph this thing, we need to isolate the y. So I'm going to add 1 to the left side of the equation, so get 2xy by itself. Divide by 2x. And then I think this is worth showing. Y1 equals, when I type this in, I would need to put parentheses around x squared minus 1, and then divided by parentheses 2x. It's common for people to, let me just show this one actually. It's common for people to type it in. Maybe you remember that you need parentheses like this. Usually we remember that, but then sometimes people just put divided by 2x. The calculator reads this as divided by 2 times x, so it puts the x, technically it would be back up in the numerator. If I graph this, you're going to see I don't get the same graph that I would have for 26 if I would have put the parentheses around. So here's another handy thing. It's not bad just to type over and put in the 2x, but if I want to insert parentheses, you can use second delete, type in your parentheses, and then arrow out of that to stop inserting spaces. Yeah, so that matches the graph. Okay, increasing and decreasing functions. Determine the open intervals. That means parentheses only, so no endpoints. When we say open interval, we're saying don't consider endpoints or turning points on which the function is increasing, decreasing, or constant. Remember to use x values only. 27 is, you have to go left to right. It's increasing the entire way. So that's for all real numbers. And that just means there's no decreasing, no constant section. 28, I listed this out as decreasing first. So from negative infinity until the vertex. The vertex looks to be at 2. You can confirm that. We did, or we will be doing like vertex formula in chapter 2, but I think you can kind of figure out that's 2 when you hit the lowest spot. So decreasing from negative infinity to 2. Increasing from 2 to infinity. There is no constant or horizontal section in there. For 29, the graph is first decreasing and then increasing. Decreasing from negative infinity until this x value, each tick mark is 1. So negative infinity to negative 1. And then increasing from positive 1 to infinity. So there's this missing chunk between plus and minus 1. And again, no constant section. None of these have a constant section looking at them. Our final graph, we're increasing, decreasing, increasing. So there are 2 sections where the graph is increasing. The first one is negative infinity to 0. Those are the x values on there. And then either use the union symbol or don't. We're not going to get counted off for that for AP. Sometimes I'll remember, sometimes I won't. The other increasing section is from 1, 2 to infinity. And the decreasing section was between 0 and 2. Again, no constant section. The next couple of problems asked us to, I'll just confirm on the page here, use a graphing utility to graph the function to approximate the relative minimum or relative maximum of the function. So I've just given you screenshots here. I will type them in and go through how to find this again. So here's g of x. So go to your y equals, clear out the old stuff, make sure your plots are off. If any of those are highlighted, go up and then unhighlight them by pressing enter. And we're typing in negative 2x to the third minus x squared plus 14x. I'm just going to zoom 6, unless it doesn't seem to fit in my window. I would like to see a little bit higher and a little bit lower. So I'm just gonna, instead of zooming out, because that zooms everything out, just bump your window up and down a little bit. Like the Y minimum maybe could be at negative 20 or something, and the Y max could be at 20. And then you just press graph. That makes it just a little taller, so that's better to see. We can see there's a relative minimum and then a relative maximum. So go to second, trace. Let's find the minimum first. You need to move your cursor, it says left bound. Move your cursor to the left of where that minimum is and press enter. Right bound means move your cursor to the right of where that minimum is and press enter. And then guess, press enter a third time so that it guesses for you. It says what is the relative minimum value. So I reported the Y coordinate because that is the minimum. The Y coordinate is the minimum. It's located at negative 1.703, but the directions didn't say ordered pair. And then for the maximum, you go to second trace, choose option 4, maximum. Get your cursor over here. I try to be kind of close to the point I'm finding. It doesn't really matter. Left and then right, and then yes. So the relative max is 12.160. Okay, and then for 48, clear out the old equation. This one is x times the square root of 4 minus x. Let's just press graph on that one. So here I can see it looks like there's a relative maximum somewhere here where we change from increasing to decreasing. So second trace, maximum, get a bit closer. So I'll press enter. I'm to the left of where I think it is. Want to make sure you get far enough to the right. There. And so this maximum we'll say is 3.079. Remember, for our AP exam, we round to 3 places for our final answers. 66 is to sketch this piecewise graph, so I've written down the g of x. So we need to know our shapes of our graphs here. We have a linear graph, x plus 5. This is only for x values that are less than or equal to negative 3. So I always begin by plugging in that end point there. So plug in negative 3 into x plus 5 and you get 2. So plot that point. This point is included on the segment. So I'm going to plot it negative 3, positive 2 with an open or with a closed circle. And then this graph is only supposed to go to the left. So we're used to saying slope of 1, up 1, right 1, up 1, right 1, but you don't want to do that because you'll be going in the wrong direction. Instead, you go down 1, left 1, down 1, left 1. So you should have this ray that's just going off to the left. And then between x equals negative 3 and 1, but not including those endpoints, the graph jumps up to a y value of just 5. So that means you could be plotting the point negative 3, 5 and 1, 5. And it's just this constant horizontal line between those 2 points. So 1, 2, 3, 4, 5. So negative 3, 5 gets an open circle here. And then 1, 5 gets an open circle, horizontal line. And finally, we have a graph that has a slope of 5 and a y-intercept of negative 4, but we're beginning at x equals 1. So if you plug 1 into that, 5 minus 4 is 1. Plot this with a closed circle because x is greater than or equal to 1 right here. So this point is on this section. 1, 1. And then I need to draw a slope of 5, or you can just plug in 2, plug in 3, whatever, to get the correct shape. I'm just going to go up 5, 1, 2, 3, 4, 5, right 1. So I'm at 2, 6. And when I draw this, from my 1, 1 point, I only go up and to the right. Piecewise functions, because they're functions, they should never cross through each other or overlap because that would cause them to fail the vertical line test. And you can see any points that are vertical from each other, one of those points is open so that you're not failing the vertical line test. Okay, a couple of word problems here we need our graphing calculators for. I've got the dimensions of my window, but I will show this as well. Let's read through the problem. The number n, which is in thousands, of new single-family houses sold each year from 2006 until 2017 in the US is approximated by this model. So they give you a domain here. That's how I knew to set my window to be 6 to 17. You'll do that for every AP problem you're given this year in pre-calc and next year in calculus. So part A is just use a graphing utility to model this graph. So first let's type it into y equals. Carefully, there's decimals and such. Remember, you can't type in x, or t, you're gonna type in x. I'm just getting this typed in. Make sure to use the subtraction sign and not, let's split screen this, and not the negative sign. Okay, so I get the equation typed in, and then I'm going to window and setting the domain, 6 for the x-min, 17 for the x-max, and it's fine to still count by ones. That's not a huge span of numbers. Instead of guessing at the y-min and y-max, because I've got this large number here, this is where you do zoom fit. So zoom, option 0, you can just press 0, or I'll just show you. It's down here. So zoom fit, zoom 0. And what that does, if you check your window again, it keeps your domain, but it changes the y values so that everything in that window from 6 to 17, every point is visible. So that's what it means by zoom fit. Okay, and then we're told to, for part B, use the graph to determine during which years the number of new single-family houses was increasing, during which years was the number decreasing. So looking at this graph, decreasing on the first section and then increasing on the second section, right? So during which years is it decreasing? I went ahead and found the minimum. Again, to do that, it would be second trace minimum. Get to the left of where that minimum point is, press enter, get to the right, press enter, guess, press enter. So that's where that number came from. So what year is that? That's 10 years. Let's see, 6 is 2006. So 10 is 2010. So this is sometime between 2010 and 2011. So determine during which years the number was of new single family houses was increasing. So I'm going to say for part B, the number of new family houses decreased from 2006 to 2010 and increased from 2010 to 2017. The change happened sometime in 2010, so it's okay to just say, you don't have to say 2010.745. And then part C is approximate the minimum number of new single family houses sold from 2006 to 2017. So I already found the minimum right there. And remember n, which is the y value, n is about equal to 308.808. That represents thousands of new single family houses. So you can either say 308.808 thousand houses, or you could multiply and just say multiply by 1,000, 308,808 houses. You just wouldn't say thousand after that. So either keep the decimal and label it thousands of houses, or multiply by 1,000. Okay, now this last one, there are different combinations you could come up with, but I just want to leave this up and kind of talk about it. So this is just to get your brain kind of thinking, and I don't know if we've got any potential engineers out there, just kind of start thinking about some of these things. So the intake pipe of a 100-gallon tank has a flow rate of 10 gallons per minute, and two drain pipes have a flow rate of 5 gallons per minute each. So we've got water coming in at 10 gallons per minute, and we've got two drains that can drain it out 5 gallons per minute each. The graph shows the volume V of the fluid in the tank as a function of time t. Determine in which pipes the fluid is flowing in specific subintervals of the 1 hour interval of time shown in the graph. So it says many correct answers. So let's just look at a couple of these. From 0 to 5, which is this first section right here, I figured out the slope just by looking at rise over run. So that slope there, we're going up 50 over 5, that's a slope of 10. So if the volume is increasing, if the volume gained 10 gallons, because that's what the Y value is, in 5 minutes, or I'm sorry, gained 50 gallons in 5 minutes, that could mean that the intake pipe was open. So we pumped in 10 gallons per minute. And it could have been that the other two were closed, right? Because 10 gallons per minute for 5 minutes, that would allow 50 gallons in. And then for the next 5 minutes, the slope is just 5. If you go 75 minus 50, 25 divided by 5, that's 5. So that still means that water's coming in, but not as fast, because one of those two drainage pipes must also be open. So water's coming in, letting water in at 10 gallons per minute, but then one of the drains is open to let it out at 5 gallons per minute, so that in 5 minutes, we got 5 more gallons. Okay, and then the last one I'll talk about here, there's just this stagnant time where a slope is 0. So the water's just sitting there for 10 minutes at the same volume. That just means all the pipes are closed. No water coming in, no water coming out. Might as well do a -1 to finish off. This slope on this next section here is -5. So you just need some combination that gives you -5. So think about that. You're losing water only, not bringing any in. So the intake valve has to be closed, and then just one of the drains has to be open. If the slope gets to -10, we would have needed both drains to be open, right? Or we could have said, I could have said drain 1 was closed and drain 2 was open. So again, that's why there are many correct answers for this problem. So just kind of something interesting, something a little bit different, just to get your brains kind of thinking differently. All right, that's it for this homework assignment. Come into office hours if you have questions or ask at the start of class.